Astronomers like big telescopes, and it's not just about bragging rights. When you look up at the night sky just with your eye, the only light that you perceive is those light rays that just happen to hit that little pupil in your eye. Well, if instead you had a bigger pupil, you could collect more light. When you look up, there's light that hits your face, that hits the ground around you. But if you could have a bigger pupil, then you could collect more light, you could see fainter objects, which means you can see further away. And if you're playing the game of looking back in time, because light takes time to cross the universe, the fainter you can see, the farther you can see, the farther back in time you can see. So we like big telescopes because they collect more light. Now let's take an example. Let's say you have a telescope that is 50 millimeters in diameter. Now that's actually that's like 2 inches. So that's like a really nice pair of binoculars or a small refractor. And so if you've got a telescope that's that big, and let's say this is the size of your pupil, I'm going to call that 5 millimeters. And this is the pupil of your eye. And this is a small telescope. And let's say that diameter is 50 millimeters. In other words, it's 10 times bigger. And the question is, how much more light does that small refractor collect than your pupil? You say 10 times bigger. You might be tempted to say, oh, it collects 10 times more light. But it's not that. It's not that, because if this is 50 and that's 5, that means I can take 10 of these pupils, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I could line them up and cross one diameter of that circle. But that doesn't account for all the area. And so really what I want to try to do is pack as many circles in there, and then keep in mind that circles don't pack, they don't nestle, you've got the gaps between, etc. So but we're trying to figure out the equivalent of how many pupils would fill that area. So what we're looking at here, trying to figure out, is what is the ratio of the areas of that circle to that circle. And so I'm going to call this, I'm going to call the telescope, I'm going to call it number 2, I'm going to call the pupil number 1. And so what we want to know is, what is A2 divided by A1? What's the area of circle 2 compared to the area of circle 1. Now the area of a circle is pi r squared. And so this ratio is pi over pi r squared, but these are different radii. So I'm going to use subscripts here, r2 and r1, to refer to the radii of circles 2 and circle 1. So we've got pi r2 squared over pi r1 squared. It's the same pi on the top and bottom, so we can cancel those, and we're left with r2 squared over r1 squared. Now just, from algebra, you've probably seen, a squared over b squared is equal to a over b quantity squared. So I can write this as r2 over r1 quantity squared. Now the ratio of the radii, though, is the same as the ratio of the diameters. In other words, the radius of this pupil in my example is 2.5 millimeters, half the diameter. The radius of this, the diameter is 50, therefore it's 25 is the radius. So 25 versus 2.5, well, that's a ratio of 10. Well, 50 versus 5 is also a ratio of 10. So in other words, I can also write this ratio as the diameter 2 over diameter 1 quantity squared. And this is our final result. This is what we're looking for, because it's saying that if this ratio, to go back to this example, if it's 10 times the diameter, this versus that, it's 10 squared, or 100 times the area, which means that it's going to collect 100 times more light. This 50 millimeter diameter telescope is equivalent to 100 eyes. If the eyes have a pupil diameter of 5 millimeters. And so that's the basic idea of comparing telescopes to, say, a pupil, or maybe even comparing 2 telescopes to each other. It's the ratio of the areas that matter, not the ratio of the diameters.